it if you have a question along the way, feel free to either unmute your mic or hit me up on chat. Let me just do a brief intro if you weren't here a couple weeks ago for the last talk. My name is Larry Landis, and I run our Fpga university program. And so I know some of your profs are using FPGAs in the classroom, and some of them might use the Intel products. Some of them might use Xilinx as another big provider of FPGA technology. So I'm kind of, I call my group sort of the 5-year marketing plan, right? Either you guys will graduate with Intel knowledge and join us, or another company and recommend our products once you get into industry. So I do a lot of training. I'm also a prof, an adjunct prof right now at Sacramento State, teaching a grad class over there. I went to CSUN. If you guys know CSUN down in LA area, I went there and graduated in 1985. So I'm an old man now. And then was working as a chip designer for a couple of years, decided to go to grad school also down in LA. Always been really excited about teaching. So I've taught at other universities besides Sac State, also at Santa Clara University. And a long time ago, I had taught an ASIC class at Cal Berkeley, and then some of my hobbies down there. So this program that I run is really about training you guys on FPGAs, hiring you, and engaging on research. So that's just why the group exists. We're about 5 or 6 people, with some partners in other countries. I work really closely with some partners in China and Korea and Europe and India as well. Okay, so basically, I put together this slide set based on a lot of stuff that I've learned over 30 years in semiconductor industry. So it's not really Intel specific. It's just to kind of tell you how this industry works and the mechanics of it and types of jobs that are available, and what's the prospects for you finding good jobs in this industry. So hopefully you'll learn a few things along the way. Let's start with Moore's Law. Hopefully everyone's heard of Moore's Law, right? Sometimes this is like the first or second lecture in a logic design type of course. So is it safe to assume that you guys have heard of Gordon Moore?
Yes.
Okay, cool. So this guy, he was working for a company called Fairchild, and he is the founder of Intel back in 1965, and came up with basically this speculation that the way things were going, that the density of transistors that we can pack onto a silicon chip will double every 18 to 24 months. And what sort of happened is the industry kind of flipped itself and said, okay, yeah, that's good, but it's not just Intel by itself that can make this happen. It's not any one company. It's a collection of people that make everything from the machinery that processes silicon wafers to the cameras, companies like Nikon and Canon. You've heard of these companies probably as camera companies, but they make equipment to build semiconductors, lots of robotics and modern silicon fabrication, so on and so forth. So all of these companies need to march along so that every couple years there's this kind of new product. And I'll show you in the next couple slides how that manifests itself in your own life. Like you hear about Moore's Law, but you're like, okay, well, how does that matter to me? Well, actually, it has a big influence in all the electronic products you buy. So what I did is I kind of looked at the level of transistor integration, okay? And this slide is a little bit old. fine. So it's going to continue up, and we're building 20 billion transistor chips at Intel in 2021, right? And what does that mean in terms of your own experience with electronic products? So I don't have the transistor counts. They used to be very publicized. They used to not be publicized, like companies wanted to keep it private. But now it's kind of this badge of honor. So what I did is I started researching what I could find on iPhones. First iPhone came out 14 years ago. Okay, it's about, I think it's September of 2007. And it wasn't that easy. I couldn't find public information on what technology node. And I'm assuming you guys have learned a little bit what this means, when we say 28 nanometer, 20 nanometer. A nanometer is a billionth of an inch, or a billionth of a meter. And so this is the key dimension of the transistor gate. And when I started doing chips, my first chip that I started designing with was 1500 nanometers. And then it went to like 1200 and 1000, and every 2 years or so, it would drop. So you can see the data that I could find started with 2012. We were doing 28 nanometer for the iPhone 5, and currently the iPhone 12 is based on 5 nanometer. And I actually was able to find the iPhone 13 data, which is a 15 billion transistor 5 nanometer product in the latest iPhones that were released, I think in August or September. And it's the same node. It's based on 5 nanometer. So they haven't moved to the next generation. The time differential between technology nodes tends to be a little bit longer. So although Moore's law keeps creeping this way, it takes longer to go from one technology node to the other just because of the laws of physics. These become very complicated and expensive to make modern silicon products. Okay, so that's just one example of how Moore's law, and maybe you guys have owned a few iPhones or Android phones in your life. Certainly you've had probably one. I'm sure everyone has a phone, but maybe you got one in high school or something like that, or maybe your parents have an old one, right? You can kind of see the features and how much better they get, right? Better graphics processing. You can do some AI. The fact that you can unlock your phone now by just it looking at you in all sorts of different directions. It's running a AI algorithm right on the phone, and looking at your face, even with glasses on and off, right? So it's a pretty smart algorithm that seems pretty hard to break. That's all running on this 15 billion transistor chip. Okay. So next thing is video games. As I'm sure all play video games, and we kind of go back to sort of start off with like Nintendo, and I guess it started off in Pong in the 70s, and it keeps moving along. These are the PlayStation technology nodes. So my former company I used to work for, a company called LSI Logic, we actually did the PlayStation 1 chip, and it was a 500 nanometer chip. I think it was running at I think it was like 33 megahertz or something. It was incredibly slow by modern standards, where processors are running 2 gigahertz and so on. But you can see kind of the visual experience from node to node, right? So if you sort of look at Mario, very pixelated, what they call aliasing, you can't really make smooth curves, gets a little bit better, more colors, and then it really starts getting into kind of modern graphics. Now you're starting to see things like, you can see which direction the light is coming from. Here, you can't see any light. Look at the shadows. Look at how the right side of Mario's hat has shadows and the left side doesn't. So you can kind of, it gives it a much more visual appeal when lighting is accurate, and it just continues to improve. these are all calculations made on the fly. So as if Mario was to turn around, the shadows would move. You can't store each, possible movement in a video game. You just have like a wireframe, and then you tell it what the shading is and what color and where the light's coming from, and it calculates it on the fly as Mario the plumber is running through the game. So this is another area where, if you think about Moore's law, forget about understanding all the physics of how semiconductors are built. It just makes life really cool that we've got these really interactive, awesome experiences that are being driven by semiconductor technology that keeps advancing. Okay. One other sort of famous law is this law that's called Amdahl's law. This one you might not have heard of, but it's kind of a computer architecture, sort of theory. That here's Moore's law picture. But the idea behind Amdahl's law is that if you add more processors, your throughput increases up to a certain point, and then it just becomes very difficult to make so many processors run in parallel and lockstep without just having bottlenecks and such. So if you think about the products that you buy now, and you walk into Best Buy or you look at your new iPhone, you not only go, well, what technology node, how fast, but you say how many processors. So, common to see 16, 32 processors, maybe a little bit more on different products. And you can see on that part of the curve, the performance and speed up is quite, it's got a pretty steep curve. Now, not every, sorry about the horn in the background. There's like a 2-year-old that seems to find the horn if you're hearing the background noise. But so anyways, you can see that there's a really good performance boost with more cores, and then it sort of becomes asymptotic, and it's just hard to write software that can take advantage of so much parallel processors, because you just get bottlenecks. Like I have to wait for this other processor to finish what it's doing before I can do anything else. And so at some point, you don't get any more return on adding more processors. Okay. So things like AI and graphics processing and things like that, they're very much based on multi-processor, technology. If you think about FPGAs and the stuff that I work on and maybe some of the labs, these are like great for, if I want to do 100 multiplies in parallel, it's quite easy to do that in an FPGA. You can go in and just, do a generate statement in Verilog or something. It'll generate 1,000 multipliers. If you can pull the data out of memory fast enough, it can do that in extremely parallel fashion. But even that, at some point, you have to get all that data back into memory, and then there'll be a bottleneck. So whether you had 500 multipliers or 1,000, you may or may not be able to get any more performance because there's bottlenecks in the system. So that's Amdahl's law. Okay, next thing is just kind of the basics about how the stuff works. You've probably seen something like this, either at the high school level or in your electronics classes at Fresno State. But there's always this common analogy that a transistor is an electronic switch, and as opposed to making it a mechanical device like your wall switch, you apply a voltage to a gate, depending on if it's NMOS or CMOS type of transistor, and current flows. So connecting a bunch of these together, which you probably learned about in terms of AND gates and OR gates and all that type of stuff, right? So I think you've seen that. Now, how tiny is this stuff? This is when 14 nanometer was kind of the modern technology of the day for Intel. Most of our new stuff is coming out in 10 nanometer or 7 nanometer. And some of the new products are coming out in 5 nanometer from TSMC in Taiwan. But you can see how tiny this is. So a coronavirus, one particular virus particle, 100 nanometers across, so it's considerably smaller than that. And frankly, not that much larger than a silicon atom. So it's kind of mind-blowing to think we're building 5 nanometer, which would only be 20 atoms wide for the gate on that. And I don't really quite understand it. You kind of have to be a PhD physics to really understand how we shrink things that small, but just appreciate it because it does make, the computing experience in our life just phenomenal, right? The stuff that we can do on a phone, on a smartwatch, and all these products is really based around trying to shrink transistors and making them really, really tiny. Kind of another look that, sort of puts everything in perspective. Pull a hair out of your scalp and you can barely see it. And that transistor at 7 nanometer is 1/10,000th the time. That dimension is 1/10,000th the size of a human hair. It's just insane. It's insane that we can build these and yield them and get them to work, but we can. And the thirst for computation is just enormous. I think we have to, thank the semiconductor industry in a big way to help us get through COVID. The fact that we can, all be video conferencing, that I can be sitting in my office here at home and very easily connect is really all because of semiconductor technology and a lot of software people to, put products together. So just think about that. The right picture, which kind of looks like sort of a dental x-ray, is the wiring. If you were to go in and cut a silicon wafer, that's the metal structures that are sort of running in horizontal and vertical direction, but you're sort of looking at it from the side. And then you see these plugs that we often call vias. Those are ways of connecting the different layers of the stack. And so you can kind of think of it like this multi-dimension freeway overpass, if you want, and how everything's connected together. Okay, next is silicon wafers. So I have one here. If I was at Fresno State, I'd pass this around and give you a lecture about not trying to bend it because they're very fragile. But it's basically, you start with this ingot of molten sand, and if I can, I'll give you something to Google if you are interested in how these are built. There's an excellent series of videos that run about maybe 30 minutes to 40 minutes, and they're quite old. I don't know, maybe Dr. Steelmaker's seen the Silicon Run videos, but they're fantastic. It's like the best explanation of how this is done. You don't need to be like a PhD in physics or chemistry or electronics to understand how it's done the way they really present it in these videos. So it's really good. It's I think they're like 1997, but a lot of the practices still hold true. So one thing I want to talk about is the silicon wafer. Let me show it one more time. Consist of, this is an 8-inch wafer. Most of them now are 12-inch wide, so they're a little bit bigger. And then you have these rectangles in here. And really what we're trying to do is design very small circuitry that make a smaller rectangle. So if you think back to your logic design course, you did stuff with K-maps. Probably everyone did Karnaugh maps at some point, right? You go and you make a truth table and you put it in this map and you kind of group them together. And if you get maybe 4 variables, you can kind of wrap your head around it. And if you get 5 variables, it's like this weird toroid, hard to figure out, but you allow the software to do it. So why do we reduce things? Well, we reduce things because we want to build things with less transistors so that I can get more little rectangles, because I go to companies like Intel or TSMC and buy these wafers. And right now, a modern wafer, I think, is like pushing maybe $10,000 a wafer, right? So you're buying these very expensive 12-inch wafers, and ideally, if you can pack, thousands, tens of thousands of silicon individual die, chop them up, and then sell them for a huge profit, right? Obviously, if it was the same function on on the right as the one on the left, the company that designed this one for that function is going to make a lot more money and win all the business because they could build it at a lower cost. Okay. So that's kind of, part of it is just to optimize things with tiny transistors. So one is to optimize like through K-maps. The other one is to use the more modern technology node, because Moore's law stated that you're basically doubling the density of transistors every 2 to 3 years now. Okay, so now there's this rush to make smaller transistors and to get really optimal, very good design techniques so that it's very optimal. The next thing is what we call gross die per wafer and net die per wafer. So you've probably seen pictures of people in semiconductor manufacturing, these manufacturing plants, and they're in these funny clothes. They often call it a bunny suit, right? And basically what they're trying to do is keep things like lint and, dandruff and flakes of skin and hair and everything out of the fabrication facility, because that stuff's like pretty light and will just float around in the air and eventually find its way landing on a silicon wafer and destroy a die that you want to go in and make it work, but it destroys that particular die. So you spend a lot of time in the fabrication world worrying about what is your yield. Okay, yield means how many die you get versus how many are broken. And so if we look at, like, here's a yield pattern for, let's say you had these sort of larger rectangles versus twice as many. So in the left case, I have 118 total die. In the right case, I have 236. If I kind of get this random pattern of stuff landing on wafer, you can't avoid it. You do not get, very rare to get 100% yield. You try, but you just can't get the clean room clean enough, especially when you're making a 5 nanometer, 7 nanometer type of chip. It just doesn't happen. Sometimes they can get 100% yield on, maybe 20-year-old technology, because what's happening is the air filtration systems and the knowledge of how to keep the dust and contaminants out. But then every time you go down, I mean, these are like atom wide, we're talking 20 atoms wide, so nothing can be around. It really has to be like zero, contaminants. So a lot of time is spent on air filtration and keeping everything clean. That's why there's so much robotics inside the manufacturing plants, because they really don't want people in there. We're dirty, right? We're very dirty. We pass viruses around to each other, and we walk around outside and carry it inside and so on. So this is a really important concept. And you can see, if I have the same defect pattern, let's say I just had, 2 die here in this pattern, none of them would work. I would get 0% yield. As I get more, I have 118, 86% of them work. If I had a smaller die, my yield would go up to 93%. Okay, so this is just a very important concept that you deal with day in, day out, working in a semiconductor company. Okay, so it gets more expensive to build these transistors. You probably hear about these billion-dollar, multi-billion-dollar investments for these fabrication plants. But at the end of the day, even though it costs more per millimeter squared of manufactured silicon, the cost per transistor continues to go down. to the right as time progresses, which is just great. Now, if this somehow bottomed out and started going up, that could be a problem. That could be a big problem. Okay, so so far it looks good. There's a path to 1 nanometer. I don't know what happens after that angstrom level integration, but yeah, it's crazy. Okay, let's go now a little bit into sort of market share. So let's just talk about companies. You know, kind of like, these are like the things that the CEO and the people, the VPs and such that report to CEOs at semiconductors think about all the time. And then we'll talk a little bit about the ecosystem and then have some time for any questions. So these are 3 words that if you've ever taken a class at a marketing class at Fresno State or at any other you know, kind of marketing course. I never did, but I learned a bunch about this stuff because I've worked in marketing quite a bit over my years in industry. But you look at things like total available market. What's the, you know, let's say you're selling silicon chips. What's the entire business of silicon chips? Right now, it's, you know, it's about $500 billion per year. And then serviceable would mean, for Intel, that means, okay, well, we sell CPUs, we're really good at that, right? We sell FPGAs, we're really good at that. So that's serviceable. That means we have a product to sell to. But there's markets that we don't do. All those analog chips and, you know, sensors and things like that, it's not really our market. So then you get into serviceable. And then, of course, you're trying to increase your market share. You know, everyone wants 100% share of market. Never happens. You know, CPUs, Intel's always kind of been top dog. AMD is starting to encroach a little bit. But we're still, you know, like 75, 80% of the market for CPUs. So we're really big. Sometimes you get companies like Google that stay dominant for a really long time. So if you think about search, I don't know, do you guys ever use Bing or other search methods? Probably not. Probably using Google. They're probably in the 90% plus share of market, right? And it's always a challenge to stay number one once you get there in these really big markets because everyone's nipping at your heels. Okay, and then the final one that's interesting is how are you growing? So this thing that we call CAGR, or compound annual growth rate, means how fast is the industry growing versus how fast is the particular company growing. And you would like to be able to beat the industry level CAGR. Okay, next thing is, this is the 2020 numbers, by the way, for different industries, right? So healthcare is the #1 industry on the planet. Okay, healthcare and insurance, and you know, this includes, I think, hospitals, and then the way they're insured and all that, is a $4.3 trillion business. And then you go down the list. So semiconductors, I don't know what number it is, but we're not in the top 10. But we're still quite a large industry, and it was $426 billion in 2020, and we're heading towards $500 billion in 2021, which starts to explain some of the shortage problems. I'll talk a little bit more about that towards the end of the talk. But you know, you picked a really good industry because, hey, 426 to 500. If you just think about, okay, for every $1 billion, I need X amount of engineers entering the industry to be able to build more products and sell more products, and then people are retiring and all that. The prospects are really good for you guys. So you made a really good decision. Maybe look at something that is probably going to drop, which is like oil and gas exploration, right? So if you look at why gas prices are so expensive, right? You know, everyone wants to kind of pin it on, you know, a president or anything like that. But the reality is, we know the Earth and everyone on the planet is seeing a shift towards green energy. And so if you're a Chevron or someone and you're saying, oh, should we be, you know, putting up these multi-billion-dollar investments to drill for more oil, when really what everyone would ultimately like is green energy, they're kind of a little bit reluctant to increase capacity. So eventually we're going to see things like, you know, oil and gas decline over the years. So, good things to think about as you're entering an industry and where you want to spend your life working at. We're in a cyclical industry. This is through 2019 of sort of the total sales per year. And sometimes it's like if you remember the housing bust, you guys were probably, I don't know, was it 12 years ago now when that happened? I'm sure your parents were grumbling about a pretty bad recession. It also meant that people weren't buying as many TVs and electronic products and such. So it was a dip year on year. And then sometimes it's just too much capacity, too many plants, manufacturing plants come online at the same time. And you have no choice. If you want market share, you have to drop your price. And so 2020, the last slide said 426, 450, somewhere in there. One of them might have been forecast. And I put, look, we're back, because 2021, we're heading towards 500 billion. So again, good news is over a long period of time, it's quite nicely up and to the right. You can look at chip stocks, go look at NVIDIA and not so much Intel, unfortunately, but AMD, all these stocks are doing quite nicely. If you look at sort of the different type of chips, FPGA is the world that I work in, which is 5 billion. I think now it's about 6 billion in 2021, something like that. So that's and growing quite nicely. But we're a pretty small portion of the overall market. The biggest one is maybe a term that you haven't heard of, but you probably know what I'm talking about once I mention it, which is ASSP, which is Application Specific Standard Product. These are things like your chips that go into networks, things that Broadcom sells, so that Cisco buys and puts it in a network switch. Ericsson might buy an ASSP that puts in their communication equipment, so on and so forth. ASIC is the same idea, but it's just one company building a custom chip for themselves to use. If you market it to many, an ASIC, which is an application-specific integrated circuit, just becomes an ASSP, if that makes sense. But you can see FPGA is small. Now, why is FPGA somewhat small? Just a sec, I want to show you something. So if you can see this little kind of acrylic block with silicon die in there. I used to work on a product for Altera. We got bought by Intel, but we make FPGAs, and then we converted them to ASICs. So the FPGAs are big. These ones on the outside of the block are FPGAs, and they're massive in terms of silicon die. This is a really big silicon die. There's not many companies that even make them that big. But once you take that function and take out all the programmability of an FPGA and just like make a custom chip, we would make these smaller die in the middle. So the reason why FPGA is small is it's just kind of difficult to put something that big into a mobile phone. So you'll end up using the FPGA to prototype and check things out, but then you're going to convert it to what we call an ASIC. And hopefully in your studies, you have, studied, usually your first class that you do is like, all right, let's go in and learn truth tables and maybe a bit on, how to create a schematic, potentially using Verilog or VHDL, one of these programming languages, and you'll learn about FPGAs. If you get a chance and you're really interested in this stuff, take the VLSI type of classes so that you understand how to build, a custom silicon chip, because there's a big market, both for FPGA designers and for custom silicon designers. But just to put it in perspective, the FPGA business is generally Intel and Xilinx. So Xilinx is the largest, and we're second, and we dominate most of the market here. Okay. This is a forecast, and let's see. So they had, this thing is amazing because 2021 predicted 500 billion, and this is in 2014. They absolutely nailed it. Whoever did the forecasting. Now they missed some of the, was a drop in 2019 where it didn't go, kind of linear as shown here. But they did a pretty good job to figure out that we're going to do well. And the growth is really nice, right? So you guys are probably going to be hitting the marketplace for, jobs in industry, probably starting in 22 and going out in the next, 1 to 4 years. And so the growth is like the curve going up is good. That means more jobs, right? And then you get a lot of, older people like me that are thinking about retirement. So when I leave, my salary probably pays for, 2 college grads to enter. So yeah, the prospects are quite good for the job market. Talk a little bit about companies. So Intel, this was so 2018 was the actual number, 2019 was the forecast number, where Intel in that year was number 1. I think we'll end up a little bit shy of 80 billion in 2021, I think is our forecast. We kind of changed places with Samsung. The reason Samsung went from 1 to 2 is because there was an oversupply of memory, and Samsung supplies a lot of memory chips, and so on and so forth. And some of these companies, you'll recognize the names, and some of them you won't, but you can look them up. This was, when this was done, it was kind of depressing because it was a pretty rough year for companies. You can see Intel was kind of immune for the oversupply of memory. But fortunes have changed. You look at some of these, NVIDIA's, totally on fire, and so on and so forth. And, you can see these percentage of change. The other thing you should note is these companies are massive. So Samsung, TSMC, SK Hynix, big numbers. And also the manufacturing is happening outside the United States, which is now a pretty big concern for the US government. So I'll talk a little bit more about some of the trends in US manufacturing, but actually spells a lot of positive news for living in the US and being an electrical engineer. This is just kind of end markets, where things are sold. I won't go into too much there. This is where the chips are being sold into, not where they're being manufactured and where the semiconductors are necessarily being built, but more what companies are selling. So that 47% would include companies like Intel, like Micron, like Broadcom, NVIDIA, AMD, right? And then Korea's got Samsung, so they're a big number. And then it kind of tails off. China is really hungry to get much bigger into the semiconductor industry, and they are spending a lot of money trying to either buy companies to get in, and they're also giving huge incentives to educators to teach more students all about semiconductor technology, so that they can, grow. And some of this tension, you hear this geopolitical tension between China and Taiwan, their neighbor across, the Taiwan Strait or whatever, right? Is that Taiwan is just crushing it on silicon technology, and China is going, okay, well, that would be one benefit of, peacefully or not peacefully having Taiwan in their domain. Okay, let's go into some other concepts. So fab versus fabless. When you're a silicon company, in the old days, you would build a company and you would manufacture your own silicon wafers, and everybody did it. There used to be this kind of motto, which was "real men have fabs." But at some point, and actually the company that I worked for prior to being acquired by Intel, Altera, were actually pretty smart. In 1984, they realized that it's pretty expensive to build one of these factories. So they just partnered up with Intel and Ricoh and these other companies that had manufacturing. And they said, we'll just do the design of the chip, but we'll send it out to a third-party company. Fast forward now, you can see the number of what we call fabless companies, right? 2005, it was only 14%, 2019, almost 30. I bet you 2021 is probably like 35%, 40%. Huge companies that are household names in semiconductors don't have manufacturing, which is kind of mind-blowing. If you think about cars, look at, Tesla. Tesla said, hey, we're going to build, electric car. We're going to design it. And of course, we're going to manufacture it, right? And, and they pulled it off. They went and used a facility actually in Fremont, California that was a GM car fab. And it's now Tesla. But where am I going with this? You can see this shift. Companies like NVIDIA, companies like AMD, a lot of Texas Instruments don't have any manufacturing. They send it out to third-party companies. And the most kind of famous one that you might have heard of is this company called Tsmc, which is totally crushing the industry of being like this big plant that, say, Apple goes to and says, hey, we need a bunch of iPhone chips and we've designed it. Here is the silicon patterns that all of what we call a mask, and there's like about 60 masks that make up a silicon chip. Unfortunately, I don't have a mask, but it's basically a piece of glass that has polygon shapes on it, and you pattern a metal layer or some other layer of the stack up to make a silicon chip. And you just send over that data over to TSMC and they'll manufacture it for you. So this is now a very great way for companies to just do the design on a very modern, leading edge silicon technology and get access to it without building a $20 billion plant that you can't afford. So the good news with me working at Intel is we're making these huge investments as well, so that part of the Intel business will be fabless. So we just broke ground about 2 months ago on a $20 billion brand new plant in the Phoenix area. And we're expanding in the US. Micron is expanding in the US. TI just announced a plant that they're going to build. I think it's a $30 billion investment in the north of Dallas. It's amazing. Like, I've never seen anything like it. The number of silicon related jobs should be really, really good. So you should be, quite happy about the job prospects. It doesn't mean everyone's just going to come knocking on your door and hire you. I mean, you have to do some work. Like I mentioned in the last talk, things are looking good. Okay, so you can see this drop, that there's only a handful of companies that are building the most latest and greatest transistor recipes, if you will. Okay, down to 5 in 2018, and there might be others that drop out. There might be just Intel, TSMC, and Samsung, and that'll be it, because no one else can afford the cost of these very expensive plants. It's just an extremely complicated business to build, a transistor that has 20 silicon atoms wide in the key feature of it. Okay, a little bit on what we do in the group I work at. So hopefully you've had a chance to program an FPGA. We have this tool set that takes languages, whether it's Verilog or VHDL or schematic, and you compiles it and you put it in this reprogrammable part. Again, we're a pretty small part of the sales out, but everybody uses them for prototyping. Okay, so if later on you're going to make a custom chip that's going to go in a phone, very likely that you're going to prototype everything in an FPGA to make sure that it works. It's hard to simulate things like CPUs. You can't really boot, Windows on a simulator very easily if you want to have every detail of 15 billion transistors worth of silicon, and you're trying to boot an operating system that in real time takes 30 seconds, and the thing's running at a gigahertz. So you can do the math, and you realize that your simulator just can't, you can't simulate anything that big. So you want to prototype it some way. So that's why you're learning about FPGAs. But that being said, we're in all sorts of, different gadgets and, just tons of different markets. I think I have a slide on that. So the way they're built is this kind of reprogrammable fabric, if you will. You have this, sort of grid of horizontal and vertical wires that you connect together to these logic blocks. The compiler figures out how to program it, and we use either a 4 or an 8 input lookup table. Basically, you write some function of 4 signals, and it can do any function of 4 inputs. If you had 6 inputs, the compiler would just go, okay, I'll split it up into 2. And if you had 100 inputs, it would just split it up into enough lookup tables to build your function. So the compiler is really smart. It's very complicated. We have hundreds of people writing the compilers for the FPGAs. And then you kind of build up that and a whole bunch of extra stuff besides the lookup tables to build a whole FPGA chip. So things that you use frequently, like multipliers and RAM and specialized interfaces, you build that with a custom interface, or sometimes you call it an ASIC style hardened interface would also become part of the chip. Okay, and then we have this Corda software that, again, hopefully you've had an opportunity to use either the Intel Corda software or the Xilinx Vivado software. They do similar things where they input a language, takes these sort of constraints about timing and where the pins are located, compile it, and build you a programming image. Okay, let's go into some other sort of dynamics. So there's been, although things have, are still growing, they're not growing at quite the rate that they were, years ago, because the industry was so brand new. It's just like, think about social media companies. It's already so big, even though it's huge. It's kind of like to grow a few percent is still, billions of dollars of net growth now for that. So things are, good, 6.7% estimated growth rate, slowing down. And because of that, if you're a smaller company, you could be target for an acquisition. So there was a bunch in 2015, including the company I was working for, Altera. We got acquired by Intel. If you've heard of ARM, ARM is the CPU that's pretty much in every mobile phone and just about any gadget, all of your Nest, let's say, these sort of IoT things that we just love, all of our cameras and such. It's likely that they have this processor called ARM, and NVIDIA is going to purchase this company. Looks like it's going to go through probably next year. It's probably in 22. This one's quite controversial, but it looks like NVIDIA is going to pull it off. And then AMD will acquire Xilinx, and that'll probably also go through next year. Some big kind of things combining. Next is kind of the other pieces of the industry. So I'll just, I talked about semiconductor industries. Now let's talk a little bit about the people that make the equipment that go into the semiconductor manufacturing plants. So here's some of the companies. Maybe you've, heard of these companies. They're not necessarily household names. Most of them are headquartered in Silicon Valley. I don't know if you go see like a San Jose Sharks hockey game, you look on the ice, sometimes you'll see these kind of company names like Applied Materials or sponsors. Like, it wouldn't make any sense to advertise at a hockey game for a semiconductor anywhere else in the country, but because it's Silicon Valley, these guys are kind of a household name, maybe in the immediate San Jose area. So they spend some money, advertising and sponsoring events and things like that. These are the companies. So again, $500 billion 2020 for these companies, growing to 2025. Look at the stock of any of these Applied Materials, Lam Research, so on and so forth, doing really well. I just bought Lam Research like a few weeks ago, and it's creeping up quite nicely. So, good areas for investment because of these giant manufacturing plants that are opening up, across the U.S. and even across the world. So that's kind of a part of the ecosystem. Is, you got the people that are selling the chips, then you got the people that are making equipment to manufacture the chips. Then you have what we call intellectual property, which is companies like ARM is the most famous one that doesn't really manufacture silicon, but they build the components that go into other people's silicon. And then they integrate an ARM processor and an Ethernet controller and a camera processor and all that, and build these custom chips. In the FPGA world, we offer all sort of these, what we call IP, intellectual property blocks. It's kind of like the idea of a package. If you have Python or a library, it's kind of equivalent to what those are in the software world. In our side of the fence of hardware, we call that IP. And sometimes these IP companies are also divisions of another piece of the business, which is called EDA, or electronic design automation. And you might have used tools from Synopsys, Cadence, Mentor, which are the big three companies that build silicon software basically to design silicon chips. So hopefully you've had a chance to, use Intel FPGAs along with tools from these companies. They also have a Silicon Valley presence as well. And if you get experience with these tools, that's really going to help your marketability as a graduating student. So try to take classes that have exposure to these software packages that, basically simulate and predict the behavior of silicon and help you design it. So this is also a growing industry, not as big as the equipment side of it, which was 60 going to 90 billion. But this is what 5.5. Let's see, 5.2 to 5.5. So it's growing a bit. Okay. All right, last, let's just kind of talk about some trends. So you've probably seen the news, right? There's just like a shortage of lots of stuff, and chips is on the top of the list of what people are feeling. And, like this kind of hits home for America. Like we love our Ford F-150s, and they had to cut production of the F-150 because they couldn't get enough chips. COVID came along, people were thinking a huge recession. They stopped investing. Turned out everyone needed more electronics to be able to do work from home. Then the car business started picking back up. And by then, the companies didn't have enough capacity. And because chips are complicated and automobiles are complicated, there's so many pieces. All it takes is one missing component to build a truck. And it suddenly, you don't have enough capacity to build it. So these sort of supply chain that we've all take for granted in our everyday life, and now they're talking about we have shortages of turkeys, right? Again, these are extremely complicated, multifaceted. It's like anyone can flip a switch after a pandemic, right? The world really doesn't know how to deal with pandemics very well, apparently. But it's messed up the supply chain, including the chip industry, which is kind of good because it's getting a lot of investment. So there's a lot of big investment into the chip industry. So there is definitely a trend towards new U.S. manufacturing. Places in the US that are growing is certainly Phoenix area is getting a new fab from Intel and also from TSMC. I heard Micron is doing a big investment, and a lot of their fabs are in the Idaho area. And then Texas Instruments is building a new fab in the Dallas area. So if you want to work on that side of the business, you know, in the manufacturing plants, those are places you might want to think about looking around. So that's kind of one part of the trend. Then I would say just always new cool mobile products, right? You know, I just traded my old iPhone 8 for an iPhone 12, and it's phenomenal. It's like, it's mind blowing how awesome it is, right? I just love it. Really good battery life, you know, AI on the fly, all these great experiences. So for sure, there's always going to be great mobile products. So a lot of the chip capacity is going into mobile products that are, you know, complicated but interesting silicon design problems. The other area that's getting really big is what we call chiplets. This is an idea that you can take the chips and integrate them into a single package to get higher levels of integration. So this is really common in lots of different products, including your mobile phone. You know, you'll basically get like this substrate, they call it, and it's kind of like two chips right next to each other on a little mini PCB, and they have a high level of connectivity. Your printed circuit boards that are on your, you know, typical boards, you know, they're kind of a fiberglass material, but for connecting chips together, sometimes they use another piece of silicon because silicon is very pure, and the density of wires is considerably higher than what you can do on a fiberglass style substrate. So that's another really big trend. For Intel itself, we just got a new CEO that's, I don't know, he's probably 7 or 8 months in. We're releasing a GPU that we're going to go up against NVIDIA and AMD in this space. When we talk about this mixed fab model, we still actually build quite a bit of our products with the TSMC factories as well. And I mentioned, you know, they're talking about 15,000 new jobs because of a manufacturing plant investment. And then just kind of the final thing is there's concern about so much global semiconductor manufacturing in the Far East, which will, you know, put a lot of emphasis again in, you know, kind of build American, buy American and stuff. So very healthy environment for our industry. So just kind of wrap up, you know, the percent change in employment. This is, I don't know what year maybe they came out with this in 2019. It's growing, right? You know, it's growing faster than other occupations. And, you know, you guys picked a good place to be in studies. So, you know, get good grades, get recommendations from your profs, you know, keep an eye on job posts and such, and you should be in good shape. Any questions?
Feel free to turn on your mic and ask your question if you have it, or you can place it in the chat as well. Okay, students. Any questions? No questions at all?
I know it's a Friday afternoon and you guys are probably zoomed out like I am after a week of yet another week, and you got Thanksgiving coming up.
Yeah. All right.
So what Intel positions is currently hiring or looking for interns right now? Do you know
Yeah,
any
so
other ones?
here, let me put a post in the chat. So if you go to jobs.intel.com, that is a site where you can go and look, and if you just put in like keywords like intern or things like that. I work in the Fpga group. You could probably look for the word Fpga and find lots of positions and so on there. So generally, if you're looking around, you could put jobs.microsoft.com, jobs, wherever you think you might be able to line up a electrical engineering job is usually a pretty good starting point. Lots of companies will then extend that to Indeed or other, sort of these general purpose job posting sites as well. As I mentioned in my last talk, kind of you could start with Intel and then go, okay, who's competitors, AMD and NVIDIA, and just go to jobs.each of these companies and start searching around for opportunities for yourself.
I did have a question.
Sure.
Are you taking any resumes at the moment?
Yeah, I'll tell you where I'm actually, give me 1 second. I'll post where I am recruiting for myself, which is just a moment. Okay, so this is the link. I'll put it in the chat. It's right here. This is a program that we hire anywhere between 0 and maybe 30 to 50. Generally we're hiring now, but it's generally for summer starts. But if you're a winter graduate, we could start sooner. But it's a rotation program that goes through different disciplines within this division of Intel, and it includes things like R&D, designing chips, the stuff that you're trained for. Then there's also the support functions, right? You get customers that are designing complicated FPGAs and they need help. So we call that application engineering. People that are writing manuals, there's, training. You got marketing functions, which are, convincing potential customers to use Intel technology in their products. And then sometimes there's positions in sales, which is going out and, meeting with customers face to face and like going through block diagrams of what they're trying to build and say, hey, you got something that can do this for, $5 or whatever. So that's kind of a sales type of role. And so you go through a series of generally 4-month rotations for maybe 12 to 18 months, and then you get placed somewhere. So it's a great way, like these type of rotation programs. The program we have is fantastic. It's like a really nice community of, people that are all graduating from all around the country and sometimes even all around the world that, come and work together over the first part of your career, and you get lots of different experiences and knowledge, and then you get placed somewhere within the company. So I highly recommend it. I would have loved to have had this experience when I graduated in 1985. I ended up doing a kind of a really super low-level detailed chip job that wasn't quite for me. And then my second job was in sales, which was super fun. And just kind of learned about, I didn't know you could do this and make money as an electrical engineer, like driving around and taking clients out to lunch and things like that. So a lot of different things you can do with this degree. So yeah, just put your resume in there. Yeah. Any other questions?
This is not a question, but I think I talked to you the other day. Well, thank you for hosting this event, and thank you for sharing this insightful presentation.
Cool. All right. Yeah. Thanks, Long. Appreciate that. Appreciate you having me back. I wish I was there in person. I'm actually going to be in Fresno next week because my son lives there, so I'll be there for Thanksgiving. But hopefully you guys get a little bit of a downtime. I don't know, over the long weekend, or if you just have to catch up on all the labs that you haven't turned in yet. But have a nice little bit of break.
Well, thank you so much, Larry. Thank you once again for this opportunity for our students. Thank you, students. Thank you, Dr. Stillmaker, for joining us this afternoon. Great information. Again, we encourage you to look at those sites that Larry shared with us when it comes to job search and internship searches. great opportunities. Like I mentioned before, the students that are working there now, or ex-students that are working there now, really enjoy it and find it very gratifying. So thank you again, Larry. Have a great holiday. Have a great weekend. Thank you, everyone. All right.
All right. Thanks for hosting, you guys. Have a good one.
All right.
Be well.
Thank you so much. Have a
Okay.
great day.
Now.